In this video, we'll be exploring the reaction energy profile for AP Chemistry. Let's get started. As we discussed with the collision model, when molecules collide with sufficient force and orientation, a bond will form. To show this process graphically, we have something known as a reaction pathway diagram, which is pictured below. The x-axis of this graph represents our time, or the progress of our reaction. The left side contains only reactants because it's at the very beginning of our reaction, and then the right side contains products because it's at the very end of our reaction. The y-axis of this graph represents the potential energy of our bonds. As you'll notice, on this left side, when we only have our reactants, we have a horizontal line which denotes our starting potential energy. As we move to the right, you'll see this energy initially increase. This is due to the fact that we always have to put in some amount of energy in order to break initial bonds. If we continue following this curve, about halfway through, we're going to reach another horizontal line. This horizontal line is also the site of our maximum potential energy. This point is known as the transition state. In this state, our old bonds are going to be partially broken, and our new bonds are going to be partially formed, resulting in the creation of our products. Our products are going to have either a higher or lower amount of potential energy stored in their bonds than our reactants. Remember, the stronger our bond, the more stable it is, and the lower its potential energy. The higher the potential energy of our bond, the less stable it is. And so as shown by this graph, after our transition state, when we form our products, we're releasing a lot of energy, and we're finishing with our products having a much lower potential energy than our initial reactants. Something else I want to point out for this graph is this distinct hump in the middle. Again, you know that the upward slope represents the initial energy we have to put in to break bonds, and the downward slope represents the energy released after our new bonds form. A super important term you must know is called activation energy, and it's this Y difference in potential energy over here. The activation energy is the amount of energy it takes to go from reactants to the peak of our graph, to our transition state. It's the amount of energy we have to put in to break our initial bonds. And you'll always be able to find your activation energy by starting at your initial potential energy and going to the peak of your curve. Again, this Y difference over here, that is your activation energy. The higher your activation energy, the more energy you have to put in to kickstart a reaction. Another thing I want to talk about is the difference between an exothermic and endothermic reaction. This is what Unit 6 entirely revolves around, so we're only going to be briefly looking at it. But essentially, an exothermic reaction is a reaction which releases energy to the surroundings, and an endothermic reaction absorbs energy from the surroundings. Remember that the less energy our bonds have, the more stable they are. So an exothermic reaction means we are ending with a lower potential energy, and an endothermic reaction means we are ending with a higher potential energy. As you'll see by this graph, we are starting with this potential energy, and we're ending at a lower potential energy. So we have released energy into the surroundings, making this an exothermic reaction. And so these are the different parts of the reaction energy profile which you have to be familiar with. And these components are going to apply to every single graph of the same sort. Take, for instance, the following reaction pathway. A difference you'll notice between this and the last reaction pathway is that we see two different peaks for our curve. What this means is that we're actually now looking at the individual elementary steps for an overall reaction. We still start with our reactants all the way on the left, and on the right, we're still forming products. But directly following our first hump, that little dip over here, this is a section in which we are forming intermediates. Again, an intermediate is something we form after the first step of our elementary reaction, and we consume it in the second step. So this intermediate is never going to show up in our overall chemical equation. But the formation of this intermediate still takes X amount of activation energy, and forming it is still going to release X amount of potential energy. Something else I want you to pay attention to, the difference in potential energy between our initial reactants and our intermediate is actually a positive value. That means that the first step, the formation of our intermediates for this reaction, is an endothermic step. If we continue, however, the difference in potential energy between our initial reactants and our final products is overall negative. Meaning that although we do have at least one endothermic step, overall, this is still going to be an exothermic reaction. So that's just another thing to keep in mind, that your individual elementary steps can have different properties from one another and from the overall reaction. One last thing we have to be able to identify for elementary reactions when we're given their reaction pathway is what's known as the rate determining step. In case you've forgotten, each of our elementary reaction steps proceeds at different speeds. Some steps are going to happen very quickly, while others are going to take longer. And our overall reaction can only go as fast as the slowest step, which is why we name that the rate determining step. The rate determining step is the slowest step in our reaction. Based off of this graph, which step do you think is going to be our rate determining step? It's going to be this one here, our first step. Why? This is a very big activation energy. If we look at our second step, however, that hump, the potential energy for our reactants is actually over here because we're starting with our intermediates. And the potential energy to get to the transition state is all the way up here. And so as you can see, that's a much smaller activation energy. So again, the rate determining step is going to be the one with the highest activation energy. And that makes sense because the more energy we have to put into a reaction for it to proceed, the slower it's going to be overall. And then of course, one last thing I want to go over. Say we have this reaction pathway for this reaction. How does changing the temperature, concentration, or pressure of our reactants change the shape of the reaction energy profile? It will not whatsoever. And I just want to put that here over the screen so you can completely understand that. Changing these values does not change the height of our activation energy whatsoever, or the graph. Our activation energy and our graph is a fixed property of the reaction mechanism, so the diagram is always going to stay exactly the same. What does change under these conditions? Well, if we increase the temperature, more molecules are going to have enough energy to get over the activation barrier. So more molecules are going to be going through the reaction. But again, the activation energy itself isn't changing. If we increase the concentration or the pressure, we're going to increase the number of collisions. So again, theoretically, more molecules should be going through the reaction. But once again, the reaction energy profile itself, that graph, is not going to change. Only the amount of particles that can successfully get over the barrier, our activation energy, is going to change. And with that being said, that's all you have to know for the reaction energy profile for AP Chemistry. In the next video, we'll be going over catalysts and how catalysts tie into the reaction energy profile. So if you're interested in that, make sure to check that out. Thank you for watching.